All right, so we're going to work on the Unit 5 portfolio, telling distance on the surface of the globe. And this is three-dimensional geometry. And so as such, it can be a little bit tricky. I want to go through a little bit of theory first, kind of explaining the concept here. And so we're going to do a drawing. And so follow along. It's kind of explaining the worksheet a little bit. First of all, we're dealing with three-dimensional geometry. So we have an x-axis, a y-axis, and a z-axis. Okay, normally we think of the x-axis as going left and right. Okay, there we go. But in this case, this is going to be the y-axis. Okay. So think of this as the y-axis. And the x-axis is going to be kind of flat. Okay, so imagine it coming out of the screen, in and out of the screen. Okay, so the x-axis, and this is in 3 dimensions, is coming towards us and going away from us. Okay, and the z-axis is going to be vertical, straight up and down. Okay, so that's the scenario we've got here: an x, a y, and a z-axis. Okay, and as you can imagine, we can plot any point in space using this coordinate system. All right, and now I'm going to superimpose a unit sphere on here. So here we go. All right, and let's draw it in green here. So it's a sphere, not a circle. So let's draw the equator of the globe here. Now, this, as I mentioned, represents the Earth, but it's going to be a unit sphere. That is a sphere with a radius of 1. Okay. Now, when we get GPS coordinates for location on the globe, we don't use X, Y, and Z coordinates. We use latitude and longitude. Latitude is how far above or below the equator you are, and longitude is how far away from, how many degrees you are away from Greenwich, England, which is considered the 0 latitude number. By the way, one thing to note, if it says your latitude is, say, 45 degrees west, if it's west, that's negative. Negative goes into the west on the globe. The western hemisphere is all going to have negative negative longitude numbers. Okay, so let's plot here a point on the surface of our globe. Okay, and we're going to want to express this both in latitude and longitude and GPR, X, Y, and Z coordinates. So let's turn our axis on its side here. Okay. And here we go. So this is the curvature of the distance. It's not linear on the surface of the globe. All straight lines on the surface of the globe are curved. And so it's non-Euclidean geometry. Okay, but the latitude number is basically this angle right here. It's the angle formed between the ray that touches the equator and the ray that touches our location. Okay, and I'm going to call this lat. Lat LAT. Okay, and actually let's try rewriting that lat. That's a little bit better. Okay. I'm going to zoom in on this here in a little bit. Okay. So there's our latitude. Now our longitude number is measured from the zero, the prime meridian, which is in Greenwich, England, and that's considered 0 degrees. And our displacement from 0 degrees, okay, our displacement from 0 degrees is our longitude number. Okay, so let's go. Oh, wrong control. Ah, here it is. There we go. All right, and oh, wrong control again. There we go. Here we go. All right. So our longitude is given by this angle right here, this sector, if you please. Okay. This is our longitude angle. Okay, spelled L-O-N. Okay. Now let me zoom in on that part of the screen here a little bit, because we've got some work to do here. Okay. So let's zoom in on that part of the screen. I'm going to switch to yellow. Okay, so this is the GPS coordinate system. Your latitude and longitude determines your location. We need to translate this into X, Y, and Z coordinates. Okay, so here we go. But remember, we have a radius of 1. Okay, and let's decrease the size. Yeah, radius of 1. Okay, that's too much. Let's check my pen here. I'm using a brush. Okay, size, opacity is 100. Okay, that's felt tip pen. Now let's go back to the brush. Okay, we'll just live with it. All right. So here we go. So what I'm interested in is solving these right triangles. So I'm going to go straight down. Straight down. Okay. And we're going to find this length. This is a right triangle. Okay, right triangle. And if you remember your right triangle trigonometry a little bit, if this is 1, then the height of this triangle is the sine of the latitude. Okay, and that happens to be our Z coordinate. Z equals sine of the latitude. Sine of the latitude. Okay? And the base of our triangle is cosine of latitude. So let me write it at an angle. Cosine of latitude. Okay? All right, so let's go on here. Now I'm going to draw a horizontally oriented right triangle. Okay, but I'm going to draw it from cosine latitude here. So now our hypotenuse is no longer 1. Okay, Our hypotenuse is cosine latitude. Okay, here we go. All right. So this is another right triangle. Another right triangle. Okay. And the width, or if you please, or the height, if you tilt your head and look at it here, is cosine latitude times sine latitude. And that happens to be our y coordinate. So y equals cosine latitude times sine latitude, or cosine latitude, which is the hypotenuse, times the sine of the longitude. Okay, so that's our y coordinate. And we have one more coordinate to get, and that is going to be our x coordinate here, which is the base, if you please, if we tilt our head sideways at this. And this is cosine latitude times cosine longitude, and that is our x coordinate. So x, going to put it over here, cosine latitude, not enough room, x equals cosine latitude and times, that's the hypotenuse, times the cosine of the longitude. Okay. And so now we've got formulas that will convert your latitude and longitude coordinates into x, y, and z coordinates, into rectangular coordinate vectors. Okay, and that's where the formulas come from. And let's zoom out a little bit here. And you can see that hopefully fairly clearly now. All right. Now, if that makes sense, great. If not, you can still do the assignment and just use the formulas. But I thought it would be helpful to understand the formulas. Okay. So now I'm going to open a spreadsheet here. Okay, and let's do that. All right. And we're going to zoom. Maybe we're in zoom view. Yeah, zoom 100%, zoom, let's zoom 200%. Make things a little bigger here. Okay. All right, so our task now is to find the coordinates of two cities, two locations here. I find the easiest way to do that is open Google Maps. Okay, I've got Google Maps open here, and actually let me just start with a fresh Google map. Okay, and we can put in any location we want here. I'm going to use the Capitol building in Boise, right? And you can put in Boise, right? Boise Capitol. Well, yeah. And Capitol building. Okay. And that'll find it for me here. And the cool thing is once you have, and we'll zoom out here a little bit, there's the Capitol building, right? Once you have a location, you can right-click somewhere on the map, and it's got the GPS coordinates right there. Isn't that cool? So there we go. We got our GPS coordinates. So 43.61771. 43.61771. Okay, 43.61771. Make sure I got that right. 43.61771. Okay, that is the latitude. Okay, and we're doing Boise, Idaho. Okay, and the other location I was thinking of was the Opera House in Sydney. Okay. That's a well-known, iconic location here. Okay, you can just see a picture of it there. Okay, so Sydney Opera House is on a peninsula here. Again, I'm going to right-click, there are our GPS coordinates. Negative 33.856. And I forgot to write down the other one. Negative 33.856. 94. Okay. And 151.21. 151.21. 21524. Okay. And Sydney, Australia. Okay. Latitude, longitude. Go back and get that other coordinate that I missed here. Negative 116.199. Negative 116.199. Notice the longitude is negative. We're in the Western Hemisphere. Okay. 199.57. 57. Okay. Interesting, by the way, that the Sydney Opera House has a positive, and that's because it's over the what we call the international date line, which is in the middle of the Pacific. So it's actually an Eastern Hemisphere country. Australia is. Interesting. Okay, so we've got our latitude and our longitude, and now we need to figure out the x-coordinate and the y-coordinate. All right, so here we go. So we have city. Okay, and I'm going to do city, and I'm just going to type equals and highlight Boise, and equals and highlight Sydney. That way it pastes the contents of those cells. Okay, so we've got x-coordinate, y-coordinate, and z-coordinate. Okay, so let's recall our formula here. So our x-coordinate was cosine of the latitude, cosine of the longitude. Cosine latitude, cosine longitude. Now, one thing about Excel, it expects angles to be in radian measure, not degrees. Okay, so we're going to type equals cosine. And now I point to the latitude, but I need to convert that to radians. Radians. And now I'm going to point to the latitude times cosine. And I'm going to, again, type in radians. It's radians function. Longitude. Okay. And we get a Boise has a negative x-coordinate. Okay. And we can do the same thing, just copy and paste, and it automatically updates to the next row, and there's Sydney's x-coordinate. Okay, our y-coordinate is cosine latitude, sine longitude. Cosine latitude, sine longitude. So cosine, radians, got to remember that radians, latitude, times sine radians longitude. Okay, and there's our y-coordinate. Okay, and just copy and paste, and it should automatically give me the y-coordinate for Sydney. Okay, all right. So now we need a z-coordinate. The z-coordinate is determined entirely by latitude. It's the sine of the latitude. So equals sine radians of the latitude. Okay, equals sine radians. Oh, why type it again? Copy and paste. Okay. Note that the z-coordinate is positive for Boise. It's in the northern hemisphere, and negative for the z, right? And then negative for Sydney because it's in the southern hemisphere. All right. Okay, so now we've got our x, y, and z coordinates for both, And so now we're going to use the formula for the angle between two vectors. Okay. Now we've got two vectors, but the vectors have three coordinates, an x, y, and a z coordinate. Okay. And here, let's do a little bit of review here. The formula for the angle between is this. Basically, it's given as cosine of theta equals the dot product between the two vectors. Dot product, and your lesson explains what dot product is. We'll do it. And then the magnitude of v of the vectors multiplied together. Okay. Now, one cool thing about this is I can simplify this in this case. The magnitude of the vectors, these are designed to be unit vectors. The magnitude of the vectors is 1. Okay, and so really it just comes down to the dot product between v and w. And that's the cosine of the angle between them. Okay. All right, so let's go ahead and do this here. So now let's do v dot w. Okay, and here's how the dot product works. You multiply the x's, so that one times that one. You multiply the y's, and you add, and you multiply the z's. So the product of the x's plus the product of the y's plus the product of the z's. Okay, and there we go. And now we want to know the angle between these, right? The angle between these, but I'm going to give the angle between them in radians, right? Or I'm going to give the angle between the two locations in radians. And that is the default unit here. So I'm going to say theta. Actually, let's leave it lowercase. Theta, okay, equals, okay, arc cosine, or a cos. In Excel, the inverse or arc cosine is a cos, okay, and then we're going to hit that cell there, the dot product, and it has an angle between it of 1.99, almost 2 radians, right? Almost 2 radians between them. Now that's actually a pretty big angle, because remember, 2 pi radians is full circle, and this is probably about 2/3 of half way around. So that's a pretty big angle on the globe. Now to find the distance, all we need to use is this formula. You remember theta in radians is defined as arc length divided by radius, right? Or arc length is theta times r. So take the angle in radians, multiply by the radius. So what we need now is the radius of the Earth. So let's look that up. Okay. So radius of the Earth, Earth radius. Now, just so you know, that is not as straightforward a question as, oh, come on, radius. All right. It wants me to, not now. Okay. All right, Earth radius. It's not as simple a question as possible as you think. Think of spinning a water balloon, right? If you spin a water balloon really fast, the equator will stretch and the poles will compress. It'll flatten out. And that actually is what the Earth does. The Earth behaves more like a water balloon than it does a rock. Okay, it's actually molten magma. It behaves like liquid with a very thin film around it. That is the crust of the Earth. And so it actually is wider at the equator than it is at the poles by a slight. So it's not quite spherical. We call it an oblate spheroid. All right, so anyway, that said, the radius of the Earth is distance from the, okay, ranges from a maximum, see, there's how it varies, and let's do miles, 3,963 miles, to a minimum of, I have to open it to here, All right. Maximum of 3,951 miles to a minimum of 3,950. Let's see. All three values. Okay. Where'd it go here? 3,950. There we go. 3,950 to 3,959. So a difference of 9 miles, which in the great scheme of things here is not much. Let's kind of split the difference. A global average value is usually, okay, that is the average value, 3,959 miles. 3,959 miles. Let's go back to our spreadsheet here. So radius of the Earth, 3,959 miles. Okay, and so arc length, or the distance between these two locations, these two cities, is theta. So equals theta times r. Okay, and I get a distance of about 7,897 or 98 miles. Now it's good to double check here. And let's do distance between Boise and Sydney, Australia. There's a Sydney, Canada, so you might want to be specific. 7,907 miles. We came out a little bit under that, right? It all a little depends on, what part of the city you're talking about. We did it from the Capitol building to the Sydney Opera House, not from the city centers. So there's room for a little bit. Plus, there's that play in what figure do you use for the radius of the Earth. There's a little bit of play in that. Anyway, so that's the point. That's how we do it. All right. So if you need any help, don't hesitate to book a live lesson with me. If you need any help with Excel, this is my preferred method for doing this one, just because it works really well with tables. Anyway, and feel free to, you do need to print out the worksheet, and there is a little bit of work to show. Don't worry about writing out the work so much. What I'm interested in is part 4. Write a paragraph that discusses what you learned about vectors. You can put the paragraph actually thinking about it. Do part 4 right here. Part 4. Write a paragraph explaining what you learned about vectors from this portfolio. So yeah, you can do this without printing out the worksheet. Yeah. All right. Thank you, and let me know if you have any questions.